Any real body which we encounter in daily life has a finite size. In dealing with the motion of extended bodies, bodies of finite size, often the idealized model of a particle is inadequate. An extended body, in the first place, is a system of particles, and we need to consider the motion of the system as a whole. The center of mass of a system of particles will be a key concept here. We shall discuss the motion of the center of mass of a system of particles and usefulness of this concept in understanding the motion of extended bodies. A large class of problems with extended bodies can be solved by considering them to be rigid bodies. Ideally, a rigid body is a body with a perfectly definite and unchanging shape. The distances between all pairs of particles of such a body do not change. It is evident from this definition of a rigid body that no real body is truly rigid, since real bodies deform under the influence of forces. But in many situations, the deformations are negligible. In a number of situations involving bodies such as wheels, tops, steel beams, molecules, and planets, on the other hand, we can ignore that they warp, twist out of shape, bend, or vibrate, and treat them as rigid. What kind of motion can a rigid body have? Consider a rectangular block sliding down an inclined plane without any sidewise movement. The block is taken as a rigid body. Its motion down the plane is such that all the particles of the body are moving together. That is, they have the same velocity at any instant of time. The rigid body here is in pure translational motion. In pure translational motion, at any instant of time, all particles of the body have the same velocity. Consider now the rolling motion of a solid metallic or wooden cylinder down the same inclined plane. The rigid body in this problem, namely the cylinder, shifts from the top to the bottom of the inclined plane, and thus seems to have translational motion. But all its particles are not moving with the same velocity at any instant. The body, therefore, is not in pure translational motion. Its motion is translational plus something else. In order to understand what this something else is, let us take a rigid body so constrained that it cannot have translational motion. The most common way to constrain a rigid body so that it does not have translational motion is to fix it along a straight line. The only possible motion of such a rigid body is rotation. The line or fixed axis about which the body is rotating is its axis of rotation. If you look around, you will come across many examples of rotation about an axis: a ceiling fan, a potter's wheel, a giant wheel in a fair, a merry-go-round, and so on. Let's try to understand what rotation is, what characterizes rotation. You may notice that in rotation of a rigid body about a fixed axis, every particle of the body moves in a circle, which lies in a plane perpendicular to the axis and has its center on the axis. Consider the rotational motion of a rigid body about a fixed axis, the z-axis of the frame of reference. Let P1 be a particle of the rigid body, arbitrarily chosen and at a distance r1 from fixed axis. The particle P1 describes a circle of radius r1 with its center C1 on the fixed axis. The circle lies in a plane perpendicular to the axis. Consider another particle P2 of the rigid body. P2 is at a distance r2 from the fixed axis. The particle P2 moves in a circle of radius r2 and with center C2 on the axis. This circle, 2, lies in a plane perpendicular to the axis. Note that the circles described by P1 and P2 may lie in different planes. Both these planes, however, are perpendicular to the fixed axis. For any particle on the axis like P3, r equals 0. Any such particle remains stationary while the body rotates. This is expected since the axis of rotation is fixed. In some examples of rotation, However, the axis may not be fixed. A prominent example of this kind of rotation is a top spinning in place. We know from experience that the axis of such a spinning top moves around the vertical through its point of contact with the ground, sweeping out a cone. This movement of the axis of the top around the vertical is termed precession. Note, the point of contact of the top with ground is fixed. The axis of rotation of the top at any instant passes through the point of contact. Another simple example of this kind of rotation is the oscillating table fan or a pedestal fan. You may have observed that the axis of rotation of such a fan has an oscillating, sidewise, movement in a horizontal plane about the vertical through the point at which the axis is pivoted. While the fan rotates and its axis moves sidewise, this point is fixed. Thus, in more general cases of rotation, such as the rotation of a top or a pedestal fan, one point and not one line of the rigid body is fixed. In this case, the axis is not fixed, though it always passes through the fixed point. We mostly deal with the simpler and special case of rotation in which one line, that is, the axis, is fixed. Thus, for us, rotation will be about a fixed axis only unless stated otherwise. The rolling motion of a cylinder down an inclined plane is a combination of rotation about a fixed axis and translation. Thus, the something else in the case of rolling motion, which we referred to earlier, is rotational motion. The motion of a rigid body, which is not pivoted or fixed in some way, is either a pure translation or a combination of translation and rotation. The motion of a rigid body, which is pivoted or fixed in some way, is rotation. The rotation may be about an axis that is fixed, example, a ceiling fan, or moving, example, an oscillating table fan. Center of mass. What is the center of mass of a system of particles, and what is its significance? For simplicity, consider a two-particle system. Consider the line joining the two particles to be the x-axis. Let the distances of the two particles be x1 and x2, respectively, from some origin O. Let m1 and m2 be respectively the masses of the two particles. The center of mass of the system is that point C, which is at a distance x from O, where x is given by m1x, 1 plus m2x2 divided by m1 plus m2. If x can be regarded as the mass-weighted mean of x1 and x2, and if the two particles have the same mass, m1 equals m2 equals m, then x equals to x1 plus x2 divided by 2. Thus, for two particles of equal mass, the center of mass lies exactly midway between them. If we have n particles of masses m1, m2, and so on up to mn respectively, along a straight line taken as the x-axis, then by definition the position of the center of the mass of the system of particles is given by x equals to sigma mi and xi divided by sigma mi, where x1, x2, up to xn are the distances of the particles from the origin. X is also measured from the same origin. Sigma denotes summation over n particles. The summation sigma m1 equals to m, which is the total mass of the system. Suppose there are three particles not lying in a straight line. We may define the x and y axes in the plane in which the particles lie and represent the positions of the three particles by coordinates x1, y1, x2, y2, and x3, y3, respectively. Let the masses of the three particles be m1, m2, and m3, respectively. The center of mass C of the system of the three particles is defined and located by the coordinates x, y, given by x equals to m1x1 plus m2x2 plus m3x3 divided by m1 plus m2 plus m3, and y equals to m1y1 plus m2 2y, 2 plus m3y, 3 divided by m1 plus m2 plus m3. For the particles of equal mass, m equals m1 equals m2 equals m3, x equals to x1 plus x2 plus x3 divided by 3, and y equals to y1 plus y2 plus y3 divided by 3. Thus, for three particles of equal mass, the center of mass coincides with the centroid of the triangle formed by the particles. The center of mass of a system of n particles, not necessarily lying in a plane, but distributed in space, is at x, y, z, where x equals sigma mi x I divided by m, y equals to mi y I divided by m, and z equals to mi z I divided by m. Here, m equals to sigma mi, which is the total mass of the system. The index I runs from 1 to n. Mi is the mass of the ith particle, and the position of the ith particle is given by xi, y, I, z, I. Combining these equations into one equation using the notation of position vectors, let R be the position vector of the ith particle, and R be the position vector of the center of mass. They are equals to sigma mi Ri divided by m. The sum on the right-hand side is a vector sum. If the origin of the frame of reference, the coordinate system, is chosen to be the center of mass, then sigma mi Ri equals to 0 for the given system of particles. A rigid body, such as a meter stick or a flywheel, is a system of closely packed particles. The number of particles, atoms, or molecules in such a body is so large that it is impossible to carry out the summations over individual particles in these equations. Since the spacing of the particles is small, we can treat the body as a continuous distribution of mass. We subdivide the body into n small elements of mass, delta m1, delta m2, and so on up to delta mn. The ith element delta m I is taken to be located about the point xi, y, I, z, I. The coordinates of the center of mass are then approximately given by x equals to sigma delta m ix I divided by sigma delta mi, y equals to sigma delta m I divided by sigma delta m I, and z equals to sigma delta m iz I divided by sigma delta mi. As we make n bigger and bigger, and each delta m I smaller and smaller, these expressions become exact. In that case, we denote the sums over I by integrals. Thus, sigma delta m I tends to integral dm, which is equal to m, and sigma delta m ix I tends to x dm, and sigma delta m iy I tends to y dm, and sigma delta m iz I tends to z dm. Here m is the total mass of the body. The coordinates of the center of mass now are x equals to 1 by m integral x dm, y equals to 1 by m integral y dm, and z equals to 1 by m integral z dm. The vector expression equivalent to these three scalar expressions is R equals to 1 by m integral r dm. If we choose the center of mass as the origin of our coordinate system, R equal to 0, then integral r dm equals to 0. Hence we get integral x dm equals integral y dm equals integral z dm equals 0. Often we have to calculate the center of mass of homogeneous bodies of regular shapes like rings, disks, spheres, rods, etc. By a homogeneous body, we mean a body with uniformly distributed mass. By using symmetry consideration, we can easily show that the centers of mass of these bodies lie at their geometric centers. Consider a thin rod, whose width and breadth, in case the cross-section of the rod is rectangular, or radius, in case the cross-section of the rod is cylindrical, is much smaller than its length. Taking the origin to be at the geometric center of the rod and x-axis to be along the length of the rod, we can say that on account of reflection symmetry, for every element dm of the rod at x, there is an element of the same mass dm located at minus x. The net contribution of every such pair to the integral and hence the integral xdm itself is 0. The point for which the integral itself is 0 is the center of mass. Thus, the center of mass of a homogeneous thin rod coincides with its geometric center. This can be understood on the basis of reflection symmetry. The same symmetry argument will apply to homogeneous rings, disks, spheres, or even thick rods of circular or rectangular cross-section. For all such bodies, you will realize that for every element dm at a point x, y, z, one can always take an element of the same mass at the point minus x, minus y, minus z. In other words, the origin is a point of reflection symmetry for these bodies. This means that for all the above bodies, their center of mass coincides with their geometric center. Motion of center of mass. Let us now discuss the physical importance of the center of mass for a system of n particles. Consider R to be the position vector of the center of mass for a system of n particles. Then, mr equals to the sum of m1, r1 plus m2, r2 plus m3, r3 up to nrn. Differentiating the two sides of the equation with respect to time, we get m multiplied by d, r divided by dt equals to m1d, r1 divided by dt1, plus m2d, r2 divided by dt2, and so on up to m in d, rn divided by dtn. This can further be represented as mv equals to m1v1 plus m2v2 plus m3v3, and so on up to nvn, where v1, v2, and so on are the velocities of the particles, and d are divided by dt equals v is the velocity of the center of mass. Note that we assume the masses m1, m2, etc. do not change in time. We have, therefore, treated them as constants in differentiating the equations with respect to time. Differentiating the velocity equation with time, we obtain mdv divided by dt equals to m1 dv1 divided by dt plus m2 dv2 divided by dt plus, and so on up to dvn divided by dt, which can also be represented as ma equals m1a1 plus m2a2 plus, and so on up to nan, where is the acceleration of the particle, and a equals dv divided by dt is the acceleration of the center of mass of the system of particles. Now, from Newton's second law, the force acting on the first particle is given by F1 equals m1a1. The force acting on the second particle is given by F2 equals m2a2, and so on. Hence, the differentiating equation with respect to time can be written as ma equals F1 plus F2 plus, and so on up to Fn. Thus, the total mass of a system of particles times the acceleration of its center of mass is the vector sum of all the forces acting on the system of particles. Note when we talk of the force F1 on the first particle, it is not a single force, but the vector sum of all the forces on the first particle, likewise for the second particle, etc. Among these forces on each particle, there will be external forces exerted by bodies outside the system, and also internal forces exerted by the particles on one another. We know from Newton's third law that these internal forces occur in equal and opposite pairs, and in the sum of forces, their contribution is 0. Only the external forces contribute to the equation. Hence, we can rewrite the formula as ma equals F external, where F external represents the sum of all external forces acting on the particles of the system. Hence, this equation states that the center of mass of a system of particles moves as if all the mass of the system was concentrated at the center of mass and all the external forces were applied at that point. Notice, to determine the motion of the center of mass, no knowledge of internal forces of the system of particles is required. For this purpose, we need to know only the external forces. Note that we did not specify the nature of the system of particles. The system may be a collection of particles in which there may be all kinds of internal motions, or it may be a rigid body, which has either pure translational motion or a combination of translational and rotational motion. Whatever is the system and the motion of its individual particles, the center of mass moves according to the external force. Instead of treating extended bodies as single particles, we can now treat them as systems of particles. We can obtain the translational component of their motion, that is, the motion of the center of mass of the system, by taking the mass of the whole system to be concentrated at the center of mass and all the external forces on the system to be acting at the center of mass. This is the procedure that we followed earlier in analyzing forces on bodies and solving problems without explicitly outlining and justifying the procedure. We now realize that in earlier studies we assumed, without saying so, that rotational motion and or internal motion of the particles were either absent or negligible. We no longer need to do this. We have not only found the justification of the procedure we followed earlier, but we also have found how to describe and separate the translational motion of 1. A rigid body, which may be rotating as well, or 2. A system of particles with all kinds of internal motion. Consider that a projectile, following the usual parabolic trajectory, explodes into fragments midway in air. The forces leading to the explosion are internal forces. They contribute nothing to the motion of the center of mass. The total external force, namely, the force of gravity acting on the body, is the same before and after the explosion. The center of mass under the influence of the external force continues, therefore, along the same parabolic trajectory as it would have followed if there were no explosion. Linear momentum of a system of particles. T linear momentum of a particle is defined as P equals mv, and Newton's second law written in symbolic form for a single particle is F equals dp divided by dt, where F is the force on the particle. Let us consider a system of n particles with masses m1, m2, and so on up to mn respectively, and velocities v1, v2, and so on up to vn respectively. The particles may be interacting and have external forces acting on them. The linear momentum of the first particle is m1v1, and of the second particle is m2v2, and so on. For the system of n particles, the linear momentum of the system is defined to be the vector sum of all individual particles of the system, p equals p1 plus p2 plus, and so on up to pn, which can be represented as P equals m1v1 plus m2v2, and so on up to mvn. Thus, the total momentum of a system of particles is equal to the product of the total mass of the system and the velocity of its center of mass, that is P equals mv. Differentiating this with respect to time, we get dp divided by dt equals to mdv divided by dt, which is equal to ma. Here, the term dp divided by dt represents the external force, F ext. This is the statement of Newton's second law of motion extended to a system of particles. Suppose now that the sum of external forces acting on a system of particles is 0. Then dp divided by dt equals to 0, or p equals constant. Thus, when the total external force acting on a system of particles is 0, the total linear momentum of the system is constant. This is the law of conservation of the total linear momentum of a system of particles. This also means that when the total external force on the system is 0, the velocity of the center of mass remains constant. Note that on account of the internal forces, that is, the forces exerted by the particles on one another, the individual particles may have complicated trajectories. Yet, if the total external force acting on the system is 0, the center of mass moves with a constant velocity, that is, moves uniformly in a straight line like a free particle. The vector equation dp divided by dt equals 0 is equivalent to three scalar equations: px equals c1, py equals c2, and pz equals c3. Here px, py, and pz are the components of the total linear momentum vector p along the x, y, and z axes respectively. c1, c2, and c3 are constants. As an example, let us consider the radioactive decay of a moving, unstable particle, like the nucleus of radium. A radium nucleus disintegrates into a nucleus of radon and an alpha particle. The forces leading to the decay are internal to the system, and the external forces on the system are negligible. So the total linear momentum of the system is the same before and after decay. The two particles produced in the decay, the radon nucleus and the alpha particle, move in different directions in such a way that their center of mass moves along the same path along which the original decaying radium nucleus was moving. If we observe the decay from the frame of reference in which the center of mass is at rest, the motion of the particles involved in the decay looks particularly simple. The product particles move back to back with their center of mass remaining at rest. In many problems on the system of particles, as in the above radioactive decay problem, it is convenient to work in the center of mass frame rather than in the laboratory frame of reference. In astronomy, binary, double, stars is a common occurrence. If there are no external forces, the center of mass of a double star moves like a free particle. The trajectories of the two stars of equal mass looks complicated. If we go to the center of mass frame, then we find that there the two stars are moving in a circle about the center of mass, which is at rest. Note that the position of the stars have to be diametrically opposite to each other. Thus, in our frame of reference, the trajectories of the stars are a combination of I, uniform motion in a straight line of the center of mass, and the second, circular orbits of the stars about the center of mass. As can be seen from the two examples, separating the motion of different parts of a system into motion of the center of mass and motion about the center of mass is a very useful technique that helps in understanding the motion of a system. Vector product of two vectors. We are already familiar with vectors and their use in physics. An important physical quantity, work, is defined as a scalar product of two vector quantities, force and displacement. We shall now define another product of two vectors. This product is a vector. Two important quantities in the study of rotational motion, namely moment of a force and angular momentum, are defined as vector products. Definition of vector product. A vector product of two vectors A and B is a vector C such that 1. Magnitude of C equals of sine theta, where A and B are magnitudes of A and B, and theta is the angle between the two vectors. 2. C is perpendicular to the plane containing A and B. 3. If we take a right-handed screw with its head lying in the plane of A and B and the screw perpendicular to this plane, and if we turn the head in the direction from A to B, then the tip of the screw advances in the direction of C, right-handed screw rule. Alternately, if one curls up the fingers of right hand around a line perpendicular to the plane of the vectors A and B, and if the fingers are curled up in the direction from A to B, then the stretched thumb points in the direction of C. A simpler version of the right hand rule is the following. Open up your right hand palm and curl the fingers pointing from A to B. Your stretched thumb points in the direction of C. It should be remembered that there are two angles between any two vectors A and B, theta and 360 degree minus theta. While applying either of the above rules, the rotation should be taken through the smaller angle, less than 180 degree, between A and B. It is theta here. Because of the cross times used to denote the vector product, it is also referred to as cross product. Note that scalar product of two vectors is commutative as said earlier. A dot B equals B dot A. The vector product, however, is not commutative. That is, a times b is not equal to b times a. The magnitude of both a times b and b times a is the same, ab sine theta. Also, both of them are perpendicular to the plane of a and b. But the rotation of the right-handed screw in case of a times b is from a to b, whereas in case of b times a it is from b to a. This means the two vectors are in opposite directions. We have a times b equals minus b times. Another interesting property of a vector product is its behavior under reflection. Under reflection, that is, on taking the plane mirror image, we have x tends to minus x, y tends to minus y, z tends to minus z. As a result, all the components of a vector change sign, and thus, a tends to minus a, b tends to minus b, c tends to minus c. What happens to a times b under reflection? A times b tends to minus a times minus b equals a times b. Thus, a times b does not change sign under reflection. Both scalar and vector products are distributive with respect to vector addition. Thus, a times b plus c equals a times b plus a times c. We may write c equals a times b in the component form. For this, we first need to obtain some elementary cross products. 1. A times a equals 0. 0 is a null vector, that is a vector with zero magnitude. This follows, since magnitude of a times is a squared sine 0 degree, which is equal to 0. From this follow the results can be derived. I vector multiplied by I vector equals 0, j vector multiplied by j vector equals 0, and k vector multiplied by k vector equals 0. Note that the magnitude of I vector times j vector is sine 90 degrees, or 1, since I vector and j vector both have unit magnitude and the angle between them is 90 degrees. Thus, I vector times j vector is a unit vector. A unit vector perpendicular to the plane of I vector and j vector and related to them by the right-hand screw rule is k vector, hence the above result. Similarly, j vector times k vector equals I vector, and k vector times I vector equals j vector. From the rule for commutation of the cross product, it follows that j vector times I vector equals minus k vector by j vector equals minus I vector, and I vector times k vector equals minus j vector. Note if I vector, j vector, and k vector occur cyclically in the above vector product relation, the vector product is positive. If I vector, j vector, and k vector do not occur in cyclic order, the vector product is negative. Angular velocity and its relation with linear velocity. We have seen that every particle of a rotating body moves in a circle. The linear velocity of the particle is related to the angular velocity. The relation between these two quantities involves a vector product. In rotational motion of a rigid body about a fixed axis, every particle of the body moves in a circle, which lies in a plane perpendicular to the axis and has its center on the axis. Consider a typical particle at a point P of the rigid body rotating about a fixed axis, taken as the z-axis. The particle describes a circle with a center C on the axis. The radius of the circle is r, the perpendicular distance of the point P from the axis. We also show the linear velocity vector v of the particle at P. It is along the tangent at P to the circle. Let P hash be the position of the particle after an interval of time increment t. The angle PCP describes the angular displacement delta theta of the particle in time delta t. The average angular velocity of the particle over the interval delta t is delta theta divided by delta t. As delta t tends to 0, that is, takes smaller and smaller values, the ratio delta theta by delta t approaches a limit, which is the instantaneous angular velocity d theta by dt of the particle at the position P. We denote the instantaneous angular velocity by omega, the Greek letter omega. We know from our study of circular motion that the magnitude of linear velocity v of a particle moving in a circle is related to the angular velocity of the particle omega by the simple relation v equals omega r, where r is the radius of the circle. We observe that at any given instant the relation v, r equals omega applies to all particles of the rigid body. Thus, for a particle at a perpendicular distance, ri from the fixed axis, the linear velocity at a given instant v I is given by v I equals omega ri. The index I runs from 1 to n, where n is the total number of particles of the body. For particles on the axis, r equals 0, and hence v equals omega, r equals 0. Thus, particles on the axis are stationary. This verifies that the axis is fixed. Note that we use the same angular velocity omega for all the particles. We therefore refer to omega as the angular velocity of the whole body. We have characterized pure translation of a body by all parts of the body having the same velocity at any instant of time. Similarly, we may characterize pure rotation by all parts of the body having the same angular velocity at any instant of time. Note that this characterization of the rotation of a rigid body about a fixed axis is just another way of saying that each particle of the body moves in a circle, which lies in a plane perpendicular to the axis and has the center on the axis. So far, the angular velocity appears to be a scalar. In fact, it is actually a vector. We shall not justify this fact, but we shall accept it. For rotation about a fixed axis, the angular velocity vector lies along the axis of rotation and points out in the direction in which a right-handed screw would advance if the head of the screw is rotated with the body. The magnitude of this vector is omega equals d theta divided by dt referred as above. Let's look at what the vector product omega times r corresponds to. It is a vector of magnitude omega r uptack and is along the tangent to the circle described by the particle at P. The linear velocity vector v at P has the same magnitude and direction. Thus, v equals omega times r. In fact, this relation holds good even for rotation of a rigid body with one point fixed, such as the rotation of the top. In this case, r represents the position vector of the particle with respect to the fixed point taken as the origin. We note that for rotation about a fixed axis, the direction of the vector omega does not change with time. Its magnitude may, however, change from instant to instant. For the more general rotation, both the magnitude and the direction of omega from instant to instant. Angular acceleration. Let us compare rotational motion along the lines of translational motion. Analogous to the kinetic variables of linear displacement, s, and velocity, v, in translational motion, we have angular displacement, theta, and angular velocity, omega, in rotational motion. It is then natural to define in rotational motion the concept of angular acceleration in analogy with linear acceleration defined as the time rate of change of velocity in translational motion. We define angular acceleration alpha as the time rate of change of angular velocity. Thus, alpha equals d omega divided by dt. Torque and angular momentum. Let's acquaint ourselves with two physical quantities, torque and angular momentum, which are defined as vector products of two vectors. These are especially important in the discussion of motion of systems of particles, particularly rigid bodies. Moment of force, torque, the motion of a rigid body, in general, is a combination of rotation and translation. If the body is fixed at a point or along a line, it has only rotational motion. We know that force is needed to change the translational state of a body, that is, to produce linear acceleration. What is the analog of force in the case of rotational motion? Let's take the example of opening or closing of a door. A door is a rigid body which can rotate about a fixed vertical axis passing through the hinges. What makes the door rotate? It is clear that unless a force is applied, the door does not rotate. But any force does not do the job. A force applied to the hinge line cannot produce any rotation at all, whereas a force of given magnitude applied at right angles to the door at its outer edge is most effective in producing rotation. It is not the force alone, but how and where the force is applied is important in rotational motion. The rotational analog of force in linear motion is moment of force. It is also referred to as torque or couple. We can use the words moment of force and torque interchangeably. Let's first define the moment of force for the special case of a single particle. Later on, we shall extend the concept to systems of particles, including rigid bodies. We shall also relate it to a change in the state of rotational motion, that is angular acceleration of a rigid body. If a force acts on a single particle at a point P whose position with respect to the origin O is given by the position vector r, the moment of the force acting on the particle with respect to the origin O is defined as the vector product tau equals r times f. The moment of force, or torque, is a vector quantity. The symbol tau stands for the Greek letter tau. The magnitude of tau is tau equals r f sine theta, whereas the magnitude of the position vector r, that is, the length OP and f is the magnitude of force F, and theta is the angle between r and f. Moment of force has dimensions ml squared t to the power of -2. Its dimensions are the same as those of work or energy. It is, however, a very different physical quantity than work. Moment of a force is a vector, while work is a scalar. The SI unit of moment of force is Newton meter in m. The magnitude of the moment of force may be written tau equals r sine theta f, which equals r perpendicular f, or tau equals r f sine theta, which equals r f perpendicular. Where r perpendicular equals r sine theta is the perpendicular distance of the line of action of f from the origin, and f perpendicular equals f sine theta is the component of f in the direction perpendicular to r. Note that tau equals 0 if r equals 0, f equals 0, or theta equals 0 degree or 180 degree. Thus, the moment of a force vanishes if either the magnitude of the force is 0, or if the line of action of the force passes through the origin. We may note that since r times f is a vector product, properties of a vector product of two vectors apply to it. If the direction of f is reversed, the direction of the moment of force is reversed. If directions of both r and f are reversed, the direction of the moment of force remains the same. Angular momentum of a particle. Just as the moment of a force is the rotational analog of force in linear motion, the quantity angular momentum is the rotational analog of linear momentum. We shall first define angular momentum for the special case of a single particle and look at its usefulness in the context of single particle motion. We shall then extend the definition of angular momentum to systems of particles, including rigid bodies. Like moment of force, angular momentum is also a vector product. It could also be referred to as moment of linear momentum. From this term, one could guess how angular momentum is defined. Consider a particle of mass m and linear momentum p at a position r relative to the origin O. The angular momentum L of the particle with respect to the origin O is defined to be L equals r times p. The magnitude of the angular momentum vector is L equals r p sine theta, where p is the magnitude of p and theta is the angle between r and p. We may write L equals r p uptack or r uptack p, where r uptack equals or sine theta, is the perpendicular distance of the directional line of P from the origin, and P uptac equals P sine theta is the component of P in a direction perpendicular to R. We expect the angular momentum to be 0, L equals 0. If the linear momentum vanishes, P equals 0. If the particle is at the origin, R equals 0. Or if the directional line of P passes through the origin, theta equals 0 degree or 180 degree. The physical quantities, moment of a force and angular momentum, have an important relation between them. It is the rotational analog of the relation between force and linear momentum. For deriving the relation in the context of a single particle, we differentiate L equals R times P with respect to time, dl divided by dt equals d by dt multiplied by R times P. Applying the product rule for differentiation to the right-hand side, d by dt multiplied by R times P equals d, R divided by dt times P plus R times dP divided by dt. Now, the velocity of the particle is v equals d, R divided by dt, and P equals mv. Hence, d R divided by dt times P equals v times mv equals 0, as the vector product of two parallel vectors vanishes. Further, since dp divided by dt equals f, R times dp divided by dt equals R times f equals t. Hence d by dt rp taf or dl by dt taf. Thus, the time rate of change of the angular momentum of a particle is equal to the torque acting on it. This is the rotational analog of the equation F equals dP by dt, which expresses Newton's second law for the translational motion of a single particle. Torque and angular momentum for a system of particles. To get the total angular momentum of a system of particles about a given point, we need to add vectorially the angular momenta of individual particles. Thus, for a system of n particles, the total angular momentum capital L equals the sum of individual angular momentums L1 plus L2 plus L3, and so on up to Ln. That is sigma L I, where I equals 1 to n. The angular momentum of the ith particle is given by Li equals our I times pi, where our I is the position vector of the ith particle with respect to a given origin, and p equals mivi is the linear momentum of the particle. The particle has mass m, I, and velocity v, I. We may write the total angular momentum of a system of particles as capital L equals sigma L I, which equals sigma or I times pi. This is a generalization of the definition of angular momentum for a single particle to a system of particles. Hence, we get rate of change of angular momentum of the system of particles equals d capital L divided by dt equals sigma I dl divided by dt, which is equal to tau I, where tau I is the torque acting on the ith particle. Tau I equals or I times fi. The force Fi on the ith particle is the vector sum of external forces Fiext acting on the particle and the internal forces Fin exerted on it by the other particles of the system. We may therefore separate the contribution of the external and the internal forces to the total torque tau equals tau in plus tau ext, where tau ext equals sigma, or I times Fiext, and tau int equals sigma, or I times Fi int. We shall assume not only Newton's third law of motion, that is, the forces between any two particles of the system are equal and opposite, but also that these forces are directed along the line joining the two particles. In this case, the contribution of the internal forces to the total torque on the system is 0, since the torque resulting from each action-reaction pair of forces is 0. Guidas have taf int mi then and therefore taf ext. Since tau equals sigma tau I, it follows that dl divided by dt equals tau ext. Thus, the time rate of the total angular momentum of a system of particles about a point, taken as the origin of our frame of reference, is equal to the sum of the external torques, that is, the torques due to external forces acting on the system taken about the same point. Note that When we have only one particle, there are no internal forces or torques, is the rotational analog of dl divided by dt equals Fext. This equation holds good for any system of particles, whether it is a rigid body or its individual particles have all kinds of internal motion. Conservation of angular momentum. If tau ext equals 0, then the rate of change of angular momentum, dl divided by dt equals 0, and hence L equals constant. Thus, if the total external torque on a system of particles is 0, then the total angular momentum of the system is conserved, that is, remains constant. The equation for the rate of change of angular momentum is equivalent to three scalar equations: Lx equals k1, Ly equals k2, and Lz equals k3. Here k1, k2, and k3 are constants. Lx, Ly, and Lz are the components of the total angular momentum vector L along the x, y, and z axes respectively. The statement that the total angular momentum is conserved means that each of these three components is conserved. The equation for the rate of change of angular momentum is the rotational analog of the rate of change of momentum dp/dt equals 0 or p equals constant. That is the conservation law of the total linear momentum for a system of particles. This has applications in many practical situations. Equilibrium of a rigid body. Let us concentrate on the motion of rigid bodies rather than on the motion of general systems of particles. We shall recapitulate what effect the external forces have on a rigid body. The forces change the translational state of the motion of the rigid body. That is, they change its total linear momentum. But this is not the only effect the forces have. The total torque on the body may not vanish. Such a torque changes the rotational state of motion of the rigid body. That is, it changes the total angular momentum of the body in accordance with the equation dl/dt equals tau ext. A rigid body is said to be in mechanical equilibrium if both its linear momentum and angular momentum are not changing with time, or equivalently. The body has neither linear acceleration nor angular acceleration. This means 1. The total force, that is, the vector sum of the forces on the rigid body is 0. If the total force on the body is 0, then the total linear momentum of the body does not change with time. Hence the equation F1 plus F2 plus F3 and so on up to Fn equals sigma I equals 1 to n Fi equals 0 gives the condition for the rotational equilibrium of the body. One may raise a question whether the rotational equilibrium condition remains valid if the origin with respect to which the torques are taken is shifted. One can show that if the translational equilibrium condition holds for a rigid body, then such a shift of origin does not matter. That is, the rotational equilibrium condition is independent of the location of the origin about which the torques are taken. There are 6 independent conditions to be satisfied for mechanical equilibrium of a rigid body. In a number of problems, all the forces acting on the body are coplanar. Then we need only 3 conditions to be satisfied for mechanical equilibrium. 2 of these conditions correspond to translational equilibrium. The sum of the components of the forces along any 2 perpendicular axes in the plane must be 0. The third condition corresponds to rotational equilibrium. The sum of the components of the torques along any axis perpendicular to the plane of the forces must be 0. The conditions of equilibrium of a rigid body may be compared with those for a particle. Since consideration of rotational motion does not apply to a particle, only the conditions for translational equilibrium apply to a particle. Thus, for equilibrium of a particle, the vector sum of all the forces on it must be 0. Since all these forces act on the single particle, they must be concurrent. A body may be in partial equilibrium, that is, it may be in translational equilibrium and not in rotational equilibrium, or it may be in rotational equilibrium and not in translational equilibrium. Consider a light that is of negligible mass, rod AB, at the two ends A and B, of which two parallel forces, both equal in magnitude and acting along same direction, are applied perpendicular to the rod. Let C be the midpoint of AB. CA equals CB equals A. The moment of the forces at A and B will both be equal in magnitude, AF, but opposite in sense. The net moment on the rod will be zero. The system will be in rotational equilibrium, but it will not be in translational equilibrium. Sigma F not equal to zero. Consider that the force at B is reversed. Thus, we have the same rod with two forces of equal magnitude but acting in opposite directions applied perpendicular to the rod, one at end A and the other at end B. Here the moments of both the forces are equal, but they are not opposite. They act in the same sense and cause anti-clockwise rotation of the rod. The total force on the body is zero, so the body is in translational equilibrium, but it is not in rotational equilibrium. Although the rod is not fixed in any way, it undergoes pure rotation, that is, rotation without translation. A pair of forces of equal magnitude, but acting in opposite directions with different lines of action, is known as a couple or torque. A couple produces rotation without translation. When we open the lid of a bottle by turning it, our fingers are applying a couple to the lid. Another known example is a compass needle in the Earth's magnetic field. The Earth's magnetic field exerts equal forces on the north and south poles. The force on the North Pole is towards the north, and the force on the South Pole is toward the south. Except when the needle points in the north-south direction, the two forces do not have the same line of action. Thus, there's a couple acting on the needle due to the Earth's magnetic field. Consider a couple acting on a rigid body. The forces F and minus F act respectively at points B and A. These points have position vectors r1 and r2 with respect to origin O. Let us take the moments of the forces about the origin. The moment of the couple equals sum of the moments of the two forces making the couple equals r1 times minus F plus r2 times F. This is equal to r2 minus r1 times F. However, r1 plus AB equals r2. And hence AB equals R2 minus R1. The moment of the couple, therefore, is AB times F. Clearly, this is independent of the origin, the point about which we took the moments of the forces. Principle of moments. An ideal lever is essentially a light that is of negligible mass, rod pivoted at a point along its length. This point is called the fulcrum. A seesaw on the children's playground is a typical example of a lever. Two forces F1 and F2, parallel to each other and usually perpendicular to the lever, as shown here, act on the lever at distances d1 and d2 respectively from the fulcrum. The lever is a system in mechanical equilibrium. Let R be the reaction of the support at the fulcrum. R is directed opposite to the forces F1 and F2. For translational equilibrium, R minus F1 minus F2 equals 0. For considering rotational equilibrium, we take the moments about the fulcrum. The sum of moments must be 0. d1 F1 minus d2 F2 is equal to 0. Normally, the anti-clockwise, clockwise moments are taken to be positive, negative. Note that R acts at the fulcrum itself and has 0 moment about the fulcrum. In the case of the lever, force F1 is usually some weight to be lifted. It is called the load, and its distance from the fulcrum d1 is called the load arm. Force F2 is the effort applied to lift the load. Distance d2 of the effort from the fulcrum is the effort arm. Hence d1 F1 equals d2 F2, or load arm times load equals effort arm times effort. The above equation expresses the principle of moments for a lever. Incidentally, the ratio F1/F2 is called the mechanical advantage, MA. MA equals F1/F2 equals D2/D1. If the effort arm D2 is larger than the load arm, the mechanical advantage is greater than 1. Mechanical advantage greater than 1 means that a small effort can be used to lift a large load. There are several examples of a lever around you besides the seesaw. The beam of a balance is a lever. The principle of moment holds even when the parallel forces F1 and F2 are not perpendicular, but act at some angle to the lever. Center of gravity. Many of you may have the experience of balancing your notebook on the tip of a finger. Take an irregular shaped cardboard having mass M and a narrow tipped object like a pencil. You can locate by trial and error a point G on the cardboard where it can be balanced on the tip of the pencil. The cardboard remains horizontal in this position. This point of balance is the center of gravity, CG, of the cardboard. The tip of the pencil provides a vertically upward force due to which the cardboard is in mechanical equilibrium. The reaction of the tip is equal and opposite to mg, and hence the cardboard is in translational equilibrium. It is also in rotational equilibrium. If it were not so, due to the unbalanced torque, it would tilt and fall. There are torques on the cardboard due to the forces of gravity like m1g, m2g, and so on, etc., acting on the individual particles that make up the cardboard. The center of gravity of the cardboard is so located that the total torque on it due to the forces m1g, m2g, etc. is 0. If our I is the position vector of the ith particle of an extended body with respect to its center of gravity, then the torque about the center of gravity, due to the force of gravity on the particle, is tau I equals or I times mig. The total gravitational torque about the center of gravity is 0. That is, tau g equals sigma tau I equals sigma, or I times m I g equals 0. We may, therefore, define the center of gravity of a body as that point where the total gravitational torque on the body is 0. Note that g is the same for all particles, and hence it comes out of the summation. This gives, since g is non-zero, sigma m I ri equals 0. Remember that the position vectors, Ri, are taken with respect to the center of gravity. Note that if the sum is 0, the origin must be the center of mass of the body. Thus, the center of gravity of the body coincides with the center of mass in uniform gravity or gravity-free space. We note that this is true because the body being small, g does not vary from one point of the body to the other. If the body is so extended that g varies from part to part of the body, then the center of gravity and center of mass will not coincide. Basically, the two are different concepts. The center of mass has nothing to do with gravity. It depends only on the distribution of mass of the body. There is also another way of determining the center of gravity of an irregular shaped body like a cardboard. If you suspend the body from some point like the vertical line through a passes through the center of gravity. We mark the vertical AA1. We then suspend the body through other points like B and C. The intersection of the verticals gives the center of gravity. Since the body is small enough, the method allows us to determine also its center of mass. Moment of inertia. What is the analog of mass in rotational motion? Let us try to get an expression for the kinetic energy of a rotating body. We know that for a body rotating about a fixed axis, each particle of the body moves in a circle with linear velocity given by equation V I equals omega Ri. For a particle at a distance from the axis, the linear velocity is Vi equals Ri omega. The kinetic energy of motion of this particle is Ki equals half mIvi square, which is equal to half m I square omega square, where mi is the mass of the particle. The total kinetic energy K of the body is then given by the sum of the kinetic energies of individual particles. That is, K equals sigma I equals 1 to nki, which is equal to half sigma I equals 1 n mi ri square omega square. Here n is the number of particles in the body. Note omega is the same for all particles. Hence, taking omega out of the sum, kinetic energy equals half omega square sigma I equals 1 to m I ri square. We define a new parameter characterizing the rigid body, called the moment of inertia, I, given by I equals sigma I equals 1 to m I ri square. Hence, with this definition, kinetic energy equals half mv square. Here, m is the mass of the body and v is its velocity. We have already noted the analogy between angular velocity omega in respect of rotational motion about a fixed axis and linear velocity v in respect of linear motion. It is then evident that the parameter moment of inertia I is the desired rotational analog of mass in linear motion. In rotation about a fixed axis, the moment of inertia plays a similar role as mass does in linear motion. As the mass of a body resists a change in its state of linear motion, it is a measure of its inertia in linear motion. Similarly, as the moment of inertia about a given axis of rotation resists a change in its rotational motion, it can be regarded as a measure of rotational inertia of the body. It is a measure of the way in which different parts of the body are distributed at different distances from the axis. Unlike the mass of a body, the moment of inertia is not a fixed quantity, but depends on distribution of mass about the axis of rotation and the orientation and position of the axis of rotation with respect to the body as a whole. As a measure of the way in which the mass of a rotating rigid body is distributed with respect to the axis of rotation, we can define a new parameter, the radius of gyration. It is related to the moment of inertia and the total mass of the body. The moments of inertia can be represented as I equals mk square, where k has the dimension of length. For a rod, about the perpendicular axis at its midpoint, that is, k square equals L square divided by 12, which means k equals L root 12. Similarly, k equals r/2 for the circular disk about its diameter. The length k is a geometric property of the body and axis of rotation. It is called the radius of gyration. The radius of gyration of a body about an axis may be defined as the distance from the axis of a mass point whose mass is equal to the mass of the whole body and whose moment of inertia is equal to the moment of inertia of the body about the axis. Thus, the moment of inertia of a rigid body depends on the mass of the body, its shape and size, distribution of mass about the axis of rotation, and the position and orientation of the axis of rotation. The dimensions of moments of inertia are ml square, and its SI units are kgm square. The property of this extremely important quantity I, as a measure of rotational inertia of the body, has been put to a great practical use. The machines, such as steam engine and the automobile engine, etc., that produce rotational motion have a disk with a large moment of inertia called a flywheel. Because of its large moment of inertia, the flywheel resists the sudden increase or decrease of the speed of the vehicle. It allows a gradual change in the speed and prevents jerky motions, thereby ensuring a smooth ride for the passengers on the vehicle. Kinematics of rotational motion about a fixed axis. The analogy between rotational motion and translational motion. For example, the angular velocity omega plays the same role in rotation as the linear velocity v in translation. Taking this analogy further, so we shall restrict the discussion only to rotation about fixed axis. This case of motion involves only one degree of freedom, that is, needs only one independent variable to describe the motion. This in translation corresponds to linear motion. For specifying the angular displacement of the rotating body, we take any particle like p of the body. Its angular displacement theta in the plane it moves is the angular displacement of the whole body. Theta is measured from a fixed direction in the plane of motion of p, which we take to be the x-axis, chosen parallel to the x-axis. Note that the axis of rotation is the z-axis and the plane of the motion of the particle is the xy plane. Let theta 0, the angular displacement at t equals 0. Consider that the angular velocity is the time rate of change of angular displacement. Omega equals d theta slash dt. Consider that the angular velocity is the time rate of change of angular displacement. Omega equals d theta slash dt. Note, since the axis of rotation is fixed, there is no need to treat angular velocity as a vector. Further, the angular acceleration, alpha equals d omega slash dt. The kinematical quantities in rotational motion, angular displacement, theta, angular velocity, omega, and angular acceleration, alpha, respectively are analogous to kinematic quantities in linear motion, displacement x, velocity v, and acceleration a. We know the kinematical equations of linear motion with uniform, that is constant, acceleration. V equals v0 plus at, and x equals x0 plus v0t plus half at square, and also v square equals v0 square plus 2ax, where x0 equals initial displacement and v0 equals initial velocity. The word initial refers to values of the quantities at t equals 0. The corresponding kinematic equations for rotational motion with uniform angular acceleration are omega equals omega 0 plus alpha t and theta equals theta 0 plus omega 0 t plus half alpha t square. And also omega square equals omega 0 square plus 2 alpha multiplied by theta minus theta 0, where theta 0 equals initial angular displacement of the rotating body, and omega 0 equals initial angular velocity of the body. Dynamics of rotational motion about a fixed axis. In rotational motion, moment of inertia and torque play the same role as mass and force respectively in linear motion. We also know that in linear motion, work done is given by F dx. In rotational motion about a fixed axis, it should be tau d theta. Since we already know the correspondence dx tends to d theta and F tends to tau. It is, however, necessary that these correspondences are established on sound dynamical considerations. We also note a simplification that arises in the case of rotational motion about a fixed axis. Since the axis is fixed, only those components of torques which are along the direction of the fixed axis need to be considered in our discussion. Only these components can cause the body to rotate about the axis. A component of the torque perpendicular to the axis of rotation will tend to turn the axis from its position. We specifically assume that there will arise necessary forces of constraint to cancel the effect of the perpendicular components of the external torques, so that the fixed position of the axis will be maintained. The perpendicular components of the torques therefore need not be taken into account. This means that for our calculation of torques on a rigid body, 1, we need to consider only those forces that lie in planes perpendicular to the axis. Forces which are parallel to the axis will give torques perpendicular to the axis and need not be taken into account. 2, we need to consider only those components of the position vectors which are perpendicular to the axis. Components of position vectors along the axis will result in torques perpendicular to the axis and need not be taken into account. Work done by a torque. Consider a rigid body rotating about a fixed axis, which is taken as the z-axis perpendicular to the plane of the page. Let's consider only those forces which lie in planes perpendicular to the axis. Let F1 be one such typical force acting as shown on a particle of the body at point P1 with its line of action in a plane perpendicular to the axis. For convenience, we call this to be the x hash, y hash plane coincident with the plane of the page. The particle at P1 describes a circular path of radius r1 with center C on the axis. Cp1 equals r1. In time delta t, the point moves to the position P1 hash. The displacement of the particle ds1, therefore, has magnitude ds1 equals r1 d theta and direction tangential at P1 to the circular path. Here d theta is the angular displacement of the particle. D theta equals angle P1 Cp1 hash. The work done by the force on the particle is dw1 equals F1. ds1 equals F1 ds1 cos1 equals F1 r1 d theta sine alpha 1, where phi 1 is the angle between F1 and the tangent at P1, and alpha 1 is the angle between F1 and the radius vector OP1. Phi 1 plus alpha 1 equals 90 degrees. The torque due to F1 about the origin is OP1 times F1. Now OP1 equals OC plus OP1. Since OC is along the axis, the torque resulting from it is excluded from our consideration. The effective torque due to F1 is tau1 equals Cp times F1. It is directed along the axis of rotation and has a magnitude tau1 equals r1 F1 sine alpha. Therefore, dw1 equals tau1 d theta. If there are more than one forces acting on the body, the work done by all of them can be added to give the total work done on the body. Denoting the magnitudes of the torques due to the different forces taf ena, taf vio, etc., dw, taf ena, taf vio, and so on, d theta. Remember, the forces giving rise to the torques act on different particles, but the angular displacement d theta is the same for all particles. Since all the torques considered are parallel to the fixed axis, the magnitude tau of the total torque is just the algebraic sum of the magnitudes of the torques, that is, tau equals tau1 plus tau2 plus, and so on. We, therefore, have dw equals tau d theta. This expression gives the work done by the total, external, torque tau, which acts on the body, rotating about a fixed axis. Its similarity with the corresponding expression dw equals fds for linear, translational, motion is obvious. Dividing both sides of the equation by dt gives p equals dw slash dt equals tau d theta slash dt equals tau omega. This is the instantaneous power. Compare this expression for power in the case of rotational motion about a fixed axis with that of power in the case of linear motion, P equals Fv. In a perfectly rigid body, there is no internal motion. The work done by external torques is therefore not dissipated and goes on to increase the kinetic energy of the body. The rate at which work is done on the body is given by P equals tau omega. This is to be equated to the rate at which kinetic energy increases. The rate of increase of kinetic energy is d divided by dt multiplied by I omega square divided by 2. We assume that the moment of inertia does not change with time. This means that the mass of the body does not change. The body remains rigid, and also the axis does not change its position with respect to the body. Since d dt alpha equals d omega slash dt, we get d divided by dt multiplied by I omega square divided by 2 equals to I omega alpha. Igeten rates of work done and of increase in kinetic energy, taf OI o alpha and taf I alpha. This equation is similar to Newton's second law for linear motion expressed symbolically as F equals ma. Just as force produces acceleration, Torque produces angular acceleration in a body. The angular acceleration is directly proportional to the applied torque and is inversely proportional to the moment of inertia of the body. Hence, this equation can be called Newton's second law for rotational motion about a fixed axis. Angular momentum in case of rotation about a fixed axis. The time rate of total angular momentum of a system of particles about a point is equal to the total external torque on the system, taken about the same point. When the total external torque is zero, the total angular momentum of the system is conserved. We now wish to study the angular momentum in the special case of rotation about a fixed axis. The general expression for the total angular momentum of the system of n particles is L equals sigma, I equals 1 to n, or I times pi. We first consider the angular momentum of a typical particle of the rotating rigid body. We then sum up the contributions of individual particles to get L of the whole body. For a typical particle, L equals R times p. The magnitude of the linear velocity v of the particle at p is given by v equals omega, r perpendicular, where r perpendicular is the length of Cp, or the perpendicular distance of p from the axis of rotation. Further, v is tangential at p to the circle which the particle describes. Using the right-hand rule, one can check that Cp times v is parallel to the fixed axis. The unit vector along the fixed axis, chosen as the z-axis, is vector k. Hence, Cp times mv equals our perpendicular mvk vector, which is equal to m r square omega k vector, since v equals omega, our perpendicular. Have you ever spun on a swivel chair and noticed something surprising? When you stretch your arms out, you slow down. When you pull your arms in, you spin faster again. This is not magic. It is one of the neat rules of motion called conservation of angular momentum. Angular momentum is the spinning version of motion. A turning object can keep its spin unless something outside pushes or twists it. If no outside torque acts on it, its angular momentum stays the same. For a body spinning in a simple way, this idea can be written as L equals I omega. Here L is angular momentum, I is moment of inertia, and omega is angular speed. The moment of inertia tells us how hard it is to change the spinning of an object. It depends on how the mass is spread out from the axis of rotation. Now, imagine a person sitting on a swivel chair with feet off the ground. If the chair turns freely and friction is very small, there's almost no outside torque about the spinning axis. So L stays constant. When the person stretches out the arms, the body spreads out farther from the axis. That makes I larger. Because L must stay the same, omega must become smaller. The spinning slows down. When the person pulls the arms close to the body, the mass moves nearer to the axis. Then I become smaller. To keep L unchanged, omega becomes larger. The person spins faster. A simple picture may help. Think of spinning ice skaters. With arms open wide, they turn more slowly. With arms pulled in, they roll quickly like tops. Divers use the same idea in the air. They tuck in to spin faster, then open up to slow down before entering the water. Dancers who perform a pirouette also use this rule with great skill. This principle is useful because it shows that spinning is not just about speed. It is also about how the mass of a body is arranged.